All right, here's another problem we're going to do truss analysis on. We want to find the forces in, let's see, we have 1, 2, 3, 4, 5, 6, 7 bars. So there's 7 unknown things, plus the reactions. All right, I think it's a good idea before we get started to kind of look at your strategy. So I'm going to suggest the first thing we do is draw a free body diagram of the whole structure and find the support reactions at E and D. Okay? Let's say we have those. Where should we go first? Well, let's ask you this question. Is there any place where there are 0 force members? Let's look at A. Is A case 1 or case 2 the way we've talked about it?
Case 1.
Case 1. So we got 2 elements connected at a point, no load. So what does that mean? That means both of these are 0. So before we even get started, 2 down. I like that. Does that create any situation anywhere else? Is there another case 1? Well, here's a case 1. Looks like it, but it has a force. So that is not a case 1. 3 bars here. 2. Oh, here's 2 bars now. But force. And up here we have 1, 2, 3. No load, but 2 are not collinear. So that's it. So we did get a couple forces. So after you would draw that, I would come over here and write it out as 0 force members, so that at least give me some idea what you're doing, and I would write that force AB is equal to force AE, and they're equal to 0.
So the questions that you ask yourself are the bars that connect, if there's a force acting on them, and if there's more than 2 bars, 2 of them have to be collinear.
Right.
Those are the only 2 questions that determine a 0 force member?
Right.
Okay.
So you look for 2 elements connecting, no load. You look for 3 elements connecting, collinear. Does it have a load? Does it not?
What about if it's more than 3?
There's no. Now, if for some reason I come along and one of these is again another 0 force member, it might create a situation where you just have 2 or 3 now that are with 2 collinear. You might create. Remember that problem we worked previously, where as we started taking it apart, we created other pieces.
What is the collinear things?
That just means they're in a line. It's a fancy word for being in the same line, collinear. Just like all of our stuff is called coplanar trusses because it's in one plane.
Maybe I just misunderstood when you were saying the example.
Start the video over.
Yeah. Okay, so let's go ahead and start. I'm going to do a free body diagram for this part of the truss, and it really doesn't matter what it looks like, but I'll kind of draw it somewhat to scale. And you can see I've already chopped those corner pieces off because they're not going to matter anyway, are they? So I'm just not even going to even draw the internal parts. I'm just going to say I know at E I have an X and a Y component. Yes? Somebody have a question?
Would that still be structurally stable if you just took off AB and
It doesn't matter. I'm not worried about stability now. I mean, I've already looked at this, and this is a stable, determinate system. This is just a blob of material, and I'm finding just the supports for it. If it bothers you, I'll just go ahead and make it look like that. It doesn't really matter what the configuration is, right? All that matters is that it's pinned here, and it has a roller here, right? And it has a force here. The only thing the blob gives you are these dimensions. This was 20 feet. This was 30 feet. So what should we do to solve this problem? Yep, I think that's a good place to do it. So we'll sum moments at E. Make sure it's in equilibrium. Using my right-hand rule, dy creates positive or negative moment. Positive, so that'll be dy. What's its moment arm? 20 feet. And then this 100 kip force creates positive or negative moment. Negative. That's 100 kips. And its moment arm is 30. So it looks like dy is going to be equal to 150. And it's positive. Is that right? Yeah. Question?
Why would the moment of 100 kips not be 20 as well? Because when it
this is its distance, right? Perpendicular distance.
So whichever way the force is pulling.
Well, I'm glad you brought that up. Remember, a force acts anywhere on its line of action, creates a moment, right? So what you want is a moment arm that provides the perpendicular distance. So from E up to that line is 30. Remember,
right. I guess the 100 kips is applied at 20 feet, but the height of it is 30 feet. So I was wondering.
It's not applied at 20 feet. It's applied at C. And C is 30 feet above this line here at the bottom.
Your moment arm has to be perpendicular to the force acting upon it, right?
Yes, unless you want to do the vector mechanics version where you write the force as a vector and you pick any R along. You remember that back in statics?
So
I don't think you should do that.
So if 100 was going down, then it would be 20.
Well, that'd be in a different direction, yeah.
Okay.
Because then it would be acting along this line of action,
Gotcha.
and the perpendicular distance would be here.
Gotcha.
Okay, so we can now sum forces in the y direction. And what do we get? We have EY acting up plus DY, and what else? Nothing. So EY is equal to negative DY, which is 150, so it's negative 150. That kind of makes sense too. If you pull this truss here about, say, pivoting about D, the only way to balance it is for EY to be acting down. And then we'll finish this up by summing forces in the x direction. I'll assume to the right is positive, and that gives us EX, and then we have the 100 kip load. So that means EX is in the opposite direction, minus 100 kips. Okay? So if you pull the truss to the right, EY better pull back to the left to balance it. So now I'll put my little spacer, and we'll start going for, how many bar forces do we have left? 1, 2, 3, 4, 5. Okay, so where's a good place to start? I'm going to say let's start at D.
Yeah.
Horrible choice. Why? 1, 2, 3 unknowns. Only 2 equations. Not a good place to start. How about E?
There we go.
E is a good place to start. In fact, E is the best place to start. Why is E the best place to start? Remember, this force is already zeroed out, so we just have BE and DE, and one is in the x direction, y direction, one is in the x direction only. That should be pretty easy to solve.
Does it really matter? Because eventually, hold on, question.
It does not matter.
Because eventually you're going to figure out.
Mathematically, it does not matter. But practically, you working a problem in a 15-minute time period in the exam, find the simplest one and start there. And then go to the next simplest one. And to the next simplest one. And if you're really, really lucky, you will never have to do the hard one. Because you'll have got all the bar forces from other places. That's an interesting time to be cutting this. Why is he cutting the grass? Why is he cutting the sidewalk with a lawnmower? Oh, is that okay? I guess rakes are not efficient anymore.
Neither are blowers.
Okay. Oh, no, don't even start with blowers.
The cost of gas is low, so they figured.
Okay, so let's start with joint E. All right, so here's my free body diagram for E. I'm going to put my forces on it. I found EY was acting down 150 kips, and EX was to the left 100 kips. Okay? And then I have a tension force, DE, and I have another tension force, BE. It's going to take me longer to write the equations than it is to tell you what the answers are. Right? But I'll do it anyway. So I'll sum forces in the y direction, assuming up is positive. And what do I have? I have the force BE up and minus 150 kips down. So what is the force in BE? 150. It came out positive, so it's in tension. I'm going to assume to the right is positive, and I will sum forces in the x direction. And I have the force in DE minus the force applied, which is 100. So what is the force DE? 100. That wasn't too bad. So I'm going to take out a pen here, and I'm just going to put a little mark through that we've got those already. So I just have 1, 2, 3 things left to do. I'm still not very happy about going to B. D maybe now because I have ED, right? But I think C is the place to go next. Granted, there are other ways to solve it, but I think viewing it kind of as you might in the heat of the exam, I would suggest you try C. So there is my free body diagram. I have the applied force at C, 100 kips. I'm going to assume a tension force in CD, and I'm going to assume a tension force in BC. What is the slope of this guy? Looks like it has a rise of 15 over a run of 20. Oh, that's your friend. Because that's a what? That's a 3, 4, 5 triangle. Your author loves 3, 4, 5s. Why is that your friend? Because the components are going to be 3/5 or 4/5. It's real easy to compute. So keep that in mind. Your author will hide that in there with various kinds of dimensions, but he likes those 3, 4, 5s. And you know what? I like them too.
Yes.
Occasionally I like the 5, 12, 13.
It's all right. I'll say I'm doing that. He does do those a lot.
Okay, so looking at that, what should I solve first? Some forces in the x or some forces in the y? Well, they both have y components, only one has x components, so I would start with x. So I would sum forces in the x direction to start. So what do I have in the x direction? Well, I have, this force is negative, so I have 4/5 of BC negative plus 100 kips. So it looks like the force in BC is going to be 125. Does that sound right? Mr. Gargis, you've been the
Yes, right.
calculator so far. And then I'll come back and I will sum forces in the y direction. What do I have? Well, I have negative CD, and I have negative the y component, which is 3/5 of BC. So what's 3/5 of that? That would be 500 divided by 3. So the force in CD looks like it's going to be negative
166.67.
166.7 is good enough for me. Okay, I need to stop the video right now. Unfortunately, my video player gets a little flaky at 15 minutes, so I'm going to stop it right here for recording purposes.